Now we're going to explore the Turing machine in some depth. We start off with what I like to think of as programming tricks for Turing machines. It's not that anyone is really going to program a Turing machine, but we need to argue about what a Turing machine could do if we really needed to have it do it. That is how we argue about the capabilities of Turing machines. For example, we argue that it can simulate a real computer. Then we delve into the matter of Turing machines with less capability, but the same ability to define exactly the recursively enumerable languages. And we argue that some natural extensions of the Turing machine idea, for example, make them non-deterministic, do not add power. They still accept only the recursively enumerable languages. The conclusion I want to draw from these restrictions and extensions is that the class of recursively enumerable languages is really an important class with many definitions, and that it really does represent what can be computed by any realistic notion of what computation means. And finally, we'll look at some of the closure properties of recursive and recursively enumerable languages. The first programming trick is thinking of the tape as if it had multiple tracks. This idea enables us to describe Turing machines that do things like leave markers on their tape so they can find their way back to an important place. We get k tracks if we think of each tape symbol as a vector with k components, each component chosen from some finite alphabet. We can think of the ith component of each tape symbol as forming the ith track. Input symbols will have the blank symbol in all components but one, which then becomes the track on which the input is placed. Here's how we can visualize a Turing machine with 3 tracks. This symbol is viewed as the vector xyz, but it is really just one tape symbol. Let's suppose the input is written on track 1. Then the input symbol 0 must be thought of as the vector 0 blank blank. And the blank symbol is thought of as the vector blank blank blank. A good use of the idea of tracks is to use one track for data and another track for marks. In the marking track, almost all the tape squares have a blank value, but one or more have special symbols, the marks, that indicate a place on the tape that the Turing machine needs to find later. Here's an example. The bottom track holds the data and the top track is the marking track. This symbol xy represents a marked y. And these symbols are unmarked w and z respectively. A similar trick is to think of the state as a vector, with each component from some finite alphabet. The first component is used to control operation, what we normally think of as the state. But other components are used as a cache to hold values the Turing machine needs to remember. Typically these values are bits or tape symbols, but they can be anything as long as they are chosen from a finite alphabet. Here's an example that will illustrate the 3 tricks we talked about. The Turing machine is not really useful. All it does is copy its input over and over again, moving right on the tape. Here are the values that will appear in the control component of the state, along with the intuition about what they're supposed to be doing. In control state Q, we mark the current position, store the current input symbol in the cache component of the state, and move right. From Q, we also enter the control state P. In state P, we run to the right looking for a blank. When we find it, we deposit the symbol that we've stored in the cache on the data track, and then we move left. From state P, we also enter control state R, in which we run left looking for the mark that was left by state Q. When we find it, we remove the mark, enter state Q, and repeat the process with another symbol. A state is a vector of the form little x, capital Y. Here little x is Q, P, or R, one of the control states, and Y is the cache component. Its values are 0, 1, or B. Incidentally, we shall see that the only state P uses 0 or 1 in the cache. The other 2 states just have the blank in the cache. Thus, there are really only 4 states. Tape symbols will be vectors UV. The first component represents the marking track, so U is either X, the mark, or a B, which is no mark. The second component is the data track, so V can be either 0, 1, or B. we regard BB as the blank symbol, B0 as input symbol 0, and B1 as input symbol 1. We'll now describe the transition function of this Turing machine. But before we do, let's understand that A and B can each have the value 0 or 1, but in a rule, all occurrences of one of these letters has the same value. Thus, this is a pair of rules, one for each value of A. It says that if the control state is Q, copy whatever symbol A is on the data track into the cache. That is, this guy winds up here in the cache. The position under the head is marked X, as we see here. And the head moves right, and the control state becomes P. There are two families of rules for control state P. If the current tape symbol does not have a blank in the data track, then stay in the same state, leave the tape symbol as it is, and move right. Note that A and little b can represent either 0 or 1 independently, so there are really 4 rules represented here. When the blank symbol BB is reached, place the symbol A that is in the cache in the data track of the square currently reached. That is, the guy in the cache winds up in the data track. Go to control state R and move to the left. And here are the rules for control state R. In state R, as long as we do not see the mark in the first track, we simply move left with no change in the state or the tape symbol. When we find the square that has the mark, we do 3 things. We remove the mark, we go to control state Q, and we move to the right. We'll be at the position just to the right of where the mark was. We're back in state Q, so the whole cycle will repeat again with whichever input 0 or 1 is in the next square. Here's a motion picture. We are in control state Q with an empty or blank cache, and we're at the left end of the input 0, 1. We're going to pick up the 0 for the cache and mark the current square, going to control state P and moving right. We did all that. Now we failed to see a blank in the data track, so we'll just move right again. Now we see the blank, so we deposit the 0 in the cache and go to state R and move left. Bingo! We haven't found the mark, so we'll move left again. Now here's the mark. We remove the mark, go to control state Q, and move right. And here we are in a situation similar to that in which we started. We'll pick up the 1, mark the square we're at, and move right in state P. Here we go off on another cycle. It never ends. We keep writing 0, 1, 0, 1, 0, 1, so on the data track. We're now going to start exploring restrictions of the original Turing machine model that are powerful enough to simulate the original model, and therefore also define exactly the recursively enumerable languages. Our first restriction is a minor one compared with some of the amazingly strong restrictions we're going to mention later. But this restriction is that we can assume the tape is infinite to the right of the input only. Tape squares to the left of where the input is placed do not exist and may not be used. The Turing machine halts if it tries to move left into a non-existent square, but we shall see that in the construction that simulates a two-way infinite tape by a one-way infinite tape, that it is also possible to design a Turing machine so it never makes that mistake and never falls off the tape. Suppose we have an ordinary Turing machine with a two-way infinite tape. We want to simulate it with a one-way infinite tape. So let's call the initial position of the head square 0. Positions to the left are -1, -2, and so on, heading left, while positions to the right are +1, +2, and so on. The new Turing machine will have 2 tracks on its tape and never move left from position 0. The top track holds the positions 0, 1, 2, and so on of the original Turing machine. And in the bottom track, paired with position 0, is a special marker, a star. It is the presence of this marker that warns the new Turing machine never to go left from that point. Also on the bottom track are all the negative positions of the original Turing machine with position -I paired with position I. That is, the bottom track holds the tape to the left of position 0, but backward. Here's a picture of the new Turing machine. Its state holds the state of the original Turing machine plus a bit, U or L, that tells it whether to look at the upper or lower track to simulate a move of the original. When that bit is U, the new Turing machine moves its head in the same direction as the original, but if the bit is L, then it moves in the direction opposite to that of the original. At the first move, the marker star will be placed on the lower track. However, there is no need to modify the input symbols, since the negative positions of the original Turing machine initially hold blank, and we can treat each of the input symbols and the blank of the new Turing machine as if they had a second component that is blank. There are several other restrictions that are discussed in the text, but we're not going to cover here. It might be surprising, but if you give a pushdown automaton, even a deterministic pushdown automaton, a second stack, then it can simulate a Turing machine. The idea is that one stack holds whatever is to the left of the head, including the head position itself, with the top of the stack at the right end of the string. The second stack holds what is to the right of the head position, with the top of the stack at the left end. The two-stack PDA can figure out a move of the Turing machine. If the head moves left, then a symbol is popped off the first stack and pushed onto the second. If the head moves right, then the top symbol is moved from the second stack to the first. Moreover, an even stronger restriction on the two-stack PDA can be made in addition to determinism. The two stacks can each be a counter, that is, a stack that has only two stack symbols. And one of these symbols, the bottom marker, can only appear as the bottom symbol. Thus the stacks each act like counters. You can add one or subtract one, but you can only tell when the count is 0. You can't tell one large count from another. This comment speaks for itself. The guy who discovered this construction that lets two counters simulate a Turing machine was Patrick Fisher. He was one of the really early computer science professors and apparently attracted the attention of the Unabomber. Pat was sent an exploding package which was opened by his secretary, who was injured in the blast but fortunately survived. Now we're going to look at several extensions to the basic Turing machine that we've described. These extensions have some use when we talk about closure properties of the recursively enumerable languages, but mainly they are considered to convince you that the basic Turing machine is good enough. It captures all of what we might think of as computing by any means. That is, our goal is to simulate each of the extensions with the basic model, and thus to show that the extensions define only the recursively enumerable languages. Our first extension will allow any finite number of tapes. Then we add non-determinism. The last extension is really a demonstration of how a Turing machine can simulate a name-value store. That is, a storage system that lets us associate any value with any name. Recently, very large-scale name-value stores have become a significant factor in the big data world, with systems like Google's Bigtable. However, our purpose here is more mundane. A name-value store is the hardest part of a computer to simulate. In essence, the memory hierarchy of a computer can be thought of as a place where we store values and locations, whether the locations are memory addresses, cache addresses, or block numbers on a disk. If we can show how a Turing machine simulates a general name-value store, then we should have a good idea of how the Turing machine can simulate a real computer. A multi-tape Turing machine has k tapes for some fixed k. There is one head for each tape, and each head is positioned at one square of its own tape. To determine a move of the multi-tape Turing machine, we have to look at the tape symbol under each head as well as the state. And the action of the multi-tape Turing machine consists of a new state, a new symbol for each tape square that is scanned, and a direction for each of the heads. The heads move independently, and some heads may choose to stay where they are rather than move at a step. To simulate k-tapes, we'll use a Turing machine with a single tape, but we'll regard this tape as having two k tracks. K of the tracks are used to simulate each of the k tapes, while the other k tracks are used to mark the head position of each of the tapes. That is, These tracks are blank except for a single X in one of the squares. Here's a picture of a one-tape Turing machine simulating a two-tape Turing machine. There are 4 tracks. 2 of these tracks hold the contents of the 2 tapes, while the other 2 tracks hold only a single X each, marking the positions of the 2 tape heads. That is, the 2-tape Turing machine has the head of its first tape scanning this C, and the head of its second tape is scanning this W. I hope it is clear that the ordinary Turing machine can, to simulate one move of the 2-tape Turing machine, visit each of the X marks, store the symbols that the 2-tape Turing machine sees in cache components of its own state, and finally figure out the move of the 2-tape machine would make. The 1-tape machine then visits each of the positions with the X's again, changes symbols as the 2-tape machine would, and moves the X's to reflect the head moves of the 2-tape machine. The 1-tape machine needs to be careful to remember in a component of its own state how many X's are to its left, so it can always find them all on its own tape. But if we design the 1-tape machine to do that correctly, then it is possible for it to simulate the 2-tape machine, although it will obviously take many of its own moves to do so. Now let's look at the non-deterministic version of a Turing machine. We'll talk only about 1-tape non-deterministic machines, but the addition of several tapes along with non-determinism doesn't add power either. The basic idea is that the Turing machine is allowed to have more than one choice of move for any state tape symbol pair. Once a choice is made, then the next state, new symbol, and head direction are determined. That is, you may have several choices in the non-deterministic Turing machine, but you can't pick a state from one, a symbol from another, and a direction from the third. As for the non-deterministic finite automata and pushdown automata, the non-deterministic Turing machine is said to accept if any sequence of choices leads to an ID with an accepting state. The basic trick is to use the tape of the deterministic machine to represent a queue of IDs of the non-deterministic machine. The deterministic machine will make a systematic search of all the IDs the non-deterministic machine can reach. If it finds one with a final state, then the deterministic machine accepts. But if it never finds one, the simulation may go on forever, but the deterministic machine will never accept. Incidentally, we should start to become aware of a surprising behavior of Turing machines. Sometimes they run forever without accepting or halting. Moreover, we can't tell whether the Turing machine is going to do that or whether it will eventually halt, either accepting or not. That is, you can't tell whether a Turing machine is an algorithm. Anyway, back to our description of how the deterministic Turing machine simulates the non-deterministic. The deterministic machine needs a separate track in addition to the track that holds the IDs of the non-deterministic machine. One purpose of this track is to mark the ID that is currently at the head of the queue of IDs. And we need another mark whose job is to allow the deterministic machine to make a copy of the ID at the queue head, one symbol at a time, while it changes this ID to reflect one of the choices of moves of the non-deterministic machine. Here's a picture of what the tape of the deterministic machine looks like. On the data track, there is a sequence of IDs separated by a special symbol, $, which we assume is not a symbol that can appear in the IDs themselves. The mark X is at the $, just before the ID that is at the head of the queue. The IDs to the left of this point will never be useful again since they have already been processed, but it is more trouble to erase them from the tape than it is to just leave them there. The mark Y indicates the last position of the front ID that has been copied, with one choice of move of the non-deterministic machine. The deterministic machine will run back and forth between the Y and the first blank it sees to its right, storing the symbol under the Y in its state and depositing it at the first blank. When it returns to the Y, it moves the Y one position right until it has copied the entire ID. However, making the changes that reflect one move. The process is just a little more complex than the simple Turing machine we gave as our example of the use of multiple tracks, which ran back and forth copying its input. Here's how the deterministic machine processes the front ID on the queue. First, the deterministic machine looks for the state within the front ID. By storing the state and the symbol to its right in its own state, it now knows all the choices of moves for the non-deterministic machine. Suppose there are m choices of move. Then the deterministic machine will create m new IDs at the rear of the queue, that is, to the right of the portion of its tape currently holding IDs. The deterministic machine decides on an order for the m choices and creates an ID reflecting each choice one at a time. After creating all m, it finds the X marker and moves it to the pound sign to the right, thus moving to the next ID in the queue. However, as an exception, if the deterministic machine ever creates a new ID with an accepting state, then it accepts and halts its operation. I described the workings of the deterministic machine fairly informally, but I hope you are convinced that the deterministic machine really could be programmed to do what I suggested. That is, you could write down a delta transition function that did all the things I talked about. However, there is an additional concern that must be addressed. Can we be sure that if any sequence of choices by the non-deterministic machine leads to a final state, then the deterministic machine will eventually follow each ID in the sequence and thus will also accept? To prove that, we first observe that there is an upper bound, say k, on the number of choices of move that the non-deterministic machine has in any situation. Thus, there are at most k IDs reachable after one move, k squared reachable after 2 moves, k cubed after 3 moves, and so on. Suppose the final state is reached after n moves for some n. Then the number of IDs the deterministic machine might have to look at is at most this, which is the sum of the first n powers of k, before it sees the ID with the final state. The exact formula is not important. The point is that k is finite and n is finite, so the number of IDs examined is finite. To see this point, notice that all the IDs reachable after one move are put on the queue before any ID that is reachable by 2 moves, and all the IDs reachable by 2 moves are placed there before we get to any ID that takes 3 moves to reach, and so on. That is, the queue is organized shortest distance first. To summarize, if the non-deterministic machine accepts, it does so in n moves for some finite n. Therefore, the deterministic machine will eventually construct the accepting ID of the non-deterministic machine, even though it may take a number of its own moves that is exponential in n. However, if no sequence of non-deterministic choices leads to acceptance, then the deterministic machine does not accept. Thus, the two machines define the same language. All the constructions we just showed will turn out to be quite useful in the future. We're going to have to do several important constructions involving Turing machines. When we do that, we'll assume the Turing machine that is input is as simple as possible. In particular, we'll assume it is a deterministic machine with one tape, infinite only to the right. However, when we do the simulation, we're free to use a Turing machine that is as powerful as we need. In particular, we can allow it to be non-deterministic and to have as many tapes as we need. But first, let's take up how we simulate name value stores by a Turing machine. The Turing machine will have several tapes that we'll describe later, but one of the tapes is used to hold the sequence of name value pairs. As suggested here, the format we use is to separate pairs by pound signs and to separate the name from the value by a star. We assume neither pound nor star are symbols that can appear in any name or value. A second track of this tape will be used to mark the left end of the sequence. This mark never moves, it's just there so we can find the beginning of the sequence and scan it looking for a particular name. A second tape will be used to hold the name that we want to look up. To look up the value associated with a name, use the marker to find the left end of the store. Compare each name with the name on the second tape. If we find a match, then the associated value is between the star and the next pound sign. However, one operation we need to be able to perform on a name value store is insertion. This operation is like what happens when we store into a computer's memory. When we insert name value pair NV, if there was no value previously associated with name n, then V will now be associated with n. However, if there was an old value associated with name n, then that value is replaced by v. Regardless of which case applies, the first thing we need to do is to look up the name n using the second tape to hold n as we just discussed. If we scan the entire store and we never find n, then append n star v pound sign to the right end of the store. That is a true insertion rather than a rewriting of a value. But if we find some nv prime in the store, we have to replace v prime by v. If v is shorter than v prime, then you can leave blanks to fill out the value. But the hard case is when v is longer than v prime. Here we have to shift the entire portion of the store that follows far enough to the right to make room for v. Here's how we'll do it. We use a third tape and we copy the entire portion of the first tape that is added to the right of v prime. But make sure to mark the position on the first tape that holds the star to the left of the v prime. Remember, this tape has a second track for marks. Now, write v on the first tape where v prime was. It's okay to overwrite any squares to the right of where v prime was. Then we restore the first tape by copying from the third tape everything that was copied there. The net effect is that the portion of the first tape that held data to the right of v prime has been moved right as many squares as was necessary to fit v in place of v prime. Here's a picture of the sequence of moves. First, we copy everything to the right of v prime onto tape 3. Then we overwrite v on tape 1, covering anything we have to. And then we copy tape 3 onto tape 1, positioning it to the right of whatever space v has taken. Okay, now we're going to see something of the closure properties for both the recursively enumerable languages, that is those that are defined by Turing machines that may run forever if they don't accept, and the recursive languages, those defined by Turing machines that will eventually halt without accepting if they choose not to accept the input. Each of these languages is closed under the regular expression operations union, concatenation, and star. They're also closed under reversal, intersection, and inverse homomorphism. The recursive languages, but not the recursively enumerable languages, are closed under difference and therefore complementation. The recursively enumerable languages, but not the recursive languages, are closed under homomorphisms. Let's first look at closure under union. Let L1 and L2 be languages accepted by final state by Turing machines M1 and M2 respectively. To make things simple, we're going to assume that M1 and M2 are one-tape machines with a semi-infinite tape. For the language L1 union L2, we construct a Turing machine M with two tapes. The first thing M does is to copy its input from the first tape to the second. Then M uses one tape to simulate M1 and the other tape to simulate M2. M accepts if either accepts. To show that the recursive languages are closed under union, observe that both M1 and M2 will eventually halt whether or not they accept. M will accept if either does, but if neither accepts, then M will eventually halt without accepting, so M is also an algorithm. For closure of the recursively enumerable languages under union, we don't know that M or M2 may run forever if they do not accept. If either accepts, then M will surely accept. However, if neither accepts, then M may run forever. But that is okay, since we only want to prove that L1 union L2 is recursively enumerable in this case, not necessarily recursive. We're going to use picture proofs for Turing machines quite a bit. Here's how we represent an algorithm, a Turing machine that always halts. It's just a box with two output signals, accept and reject. We should understand that reject just means that the machine halts without accepting. We know that an algorithm will eventually make one of these signals, and of course not both. Then the design of M can be expressed by this diagram. It gets its input W from the outside, and it feeds it to M1 and M2. which it then simulates. M produces the accept signal if either M1 or M2 accepts. If neither produces accept, then they eventually both produce reject, and M produces the reject signal when they both do. Thus M will make one of these signals but not both, and of course it makes the right signal to accept the union of the languages. And here's how we represent a Turing machine that is not necessarily an algorithm. It makes an accept signal if it accepts, but we cannot expect it to make a reject signal. It may just keep making moves but never accept. This diagram is the design of M for the case where M1 and M2 are general Turing machines. Again, M feeds both the input W. If either raises the accept signal, then M does too. We have no idea what M does if neither accepts, but it doesn't matter. M has the form needed to show that the union of the languages of M1 and M2 is a recursively enumerable language. Here's a picture proof of the fact that recursive languages are closed under intersection. M1 and M2 are algorithms. We design M to feed its input to the simulated M1 and M2, and M accepts if both accept, and M rejects if either rejects. And here's a picture proof for the intersection of recursively enumerable languages. Again, M feeds its input to M1 and M2, and it accepts if both accept. Now, difference and complement give us very different stories for the two classes of languages, recursive and recursively enumerable. If you want to accept the difference of the languages of algorithms M1 and M2, simulate them both until they halt. Accept if M1 accepts and M2 rejects, and otherwise reject. The picture is much like what we saw for union and intersection of recursive languages, only the logic combining the signals is different. An important consequence is that the complement with respect to some alphabet sigma of a recursive language is recursive. Surely sigma star, the set of all strings over sigma, is recursive. So the difference of sigma star and a recursive language is the complement of that language. Unfortunately, this approach does not work for the recursively enumerable languages. They are in fact not closed under difference or complementation. We'll see a particular recursively enumerable language whose complement is not recursively enumerable soon. But just to see why the construction for recursive languages doesn't work, remember that M2 may never halt. So if M1 accepts, we may never know that the input is in the difference. Now let's show that the recursively enumerable languages are closed under concatenation. Let L1 and L2 be defined by Turing machines M1 and M2. Assume M1 and M2 have one semi-infinite tape each. And for concatenation, we're going to construct M, a two-tape non-deterministic Turing machine. Given input W, M guesses a prefix X of W that is in L1. Then let Y be the remainder of W, which then must be in L2, that is, if W is to be in the concatenation of the languages L1 and L2. M moves Y to its second tape. M simulates M1 on input X and M2 on Y. If both accept, then M accepts. Since it is non-deterministic, it will guess every possible way to break W into two pieces, so it always accepts W if W is in L1 concatenated with L2. Next, we claim the recursive languages are also closed under concatenation. We can't use the non-deterministic trick, or at least it's rather hard to do so. However, M will systematically try each possible breakpoint for W into XY, run M1 on X and M2 on Y. M1 and M2 always halt on each X and Y. If for any breakpoint both accept their pieces, then M accepts. But if all breakpoints lead to rejection by one or both of M1 and M2, then M eventually runs out of things to try and rejects. For closure under star, the same ideas work as for concatenation. Suppose M1 is a Turing machine for some language L, and we want a Turing machine for L star. For the recursively enumerable languages, guess how many pieces to break input W into, and guess where the points of separation are, except if M1 accepts each piece. For the recursive languages, don't guess, but enumerate the breaks systematically, since M1 is guaranteed to halt anytime it is given a piece of the input W to examine. We'll eventually get through testing each of the possible ways to break the input. Reversal is easy for both classes of languages. First, reverse the input and then simulate the Turing machine for language L on the reversed input. We'll not say anything more about this simple idea. Inverse homomorphism is also quite simple. Suppose L is a language, either recursive or recursively enumerable. Let M be a Turing machine for L and let H be a homomorphism. We'll design a Turing machine for H inverse of L. We'll start by applying H to the given input W. Simulate M on H of W. Accept W if H of W is an L. If L is recursively enumerable, then we've got a Turing machine which may not always halt for H inverse of L. But if L is recursive, then we know M will always halt, and thus so will the machine we just designed. Last, let's show that the recursively enumerable languages are closed on their homomorphism. So suppose L has a Turing machine M1. We'll construct a non-deterministic Turing machine M for H of L. Given input W, M guesses a string X and checks that H of X is W. If so, M simulates M1 on input X. If M1 accepts X, then M accepts W. Thus, M accepts H inverse of L. This construction won't work for the recursive languages. The reason is that if H maps some symbols to epsilon, then the string X that M1 accepts may be arbitrarily long, and M may have to simulate an infinite number of possible X's. It can never be sure that there is no X in L for which H of X equals W.